Welcome to another lecture of data mining. So this week we're entering an exciting new phase, which is modeling, right? So you've already explored the data set, cleaned and transformed it, and now it's time to ask a key question, which is how can a machine learn from data to make decisions? So let's start with a question you've probably wondered about, right? How do platforms like Amazon, Netflix, or Spotify know what to recommend before you even ask, right? So behind these everyday interactions are actually data mining models that have learned patterns from massive amounts of past behavior. So these models don't just store data, they learn from it to make predictions or to discover structure. And that's what we are starting this week. So now that we've prepared our data, the next step is to build models that can extract meaningful patterns and make decisions and support smart business insights, right? So how can we teach a machine to learn from data, right? That's the question. So we can think about answering this question as follows. There is many different ways a machine can learn, right? There is the supervised learning, right? And here we have a data set with input features and labeled outcomes. And for example, we might train a model to predict whether a customer will make a purchase based on age, or based on browsing history or coupon use and so on, right? So here the data is labeled, right? In contrast, we have unsupervised learning, and it's what we use when the data set actually is unlabeled. So the model's job here is to find structure. So for example, grouping customers into behavioral groups without knowing in advance which group is which, right? That's unsupervised learning. So in between, we have semi-supervised learning. So imagine you only have labels for a small portion of your data, but still want to train a model. So this approach is especially useful when labeling is expensive or time consuming. So we use semi-supervised learning to label a large, big, unlabeled data starting from a small labeled data. And then lastly, there is reinforcement learning, which is a very different approach. Here, the machine acts in an environment and learns through trial and error, guided by rewards. So think of recommendation engines that adjust based on what users click. Okay, so in this course, we'll focus mostly on supervised and unsupervised learning. So let's bring it down to the data set we've been working with, which is retail. So suppose we want to predict whether a customer will buy something. So if we already know the outcome, which is the yes or no, buy or don't buy, then we are doing supervised learning, right? But if we remove that outcome label and ask the machine to group similar customers based only on their behavior, like age, web visits, or coupon usage, as we said before, then we are entering the world of unsupervised learning. Okay. So these two answer very different questions. For the first one right here, it's answering the question of who is likely to buy, right? And then for the second one, we are answering a question like what kinds of shoppers exist. So let's take a closer look to supervised learning. So under supervised learning, there's two main categories. There is classification and there is regression. So let's start with classification learning. So classification learning is the most fundamental and widely applied techniques in data mining. You will encounter it throughout this course and well beyond. whether you are building spam filters, fraud detection systems, right? So it is a type of supervised learning, as we said. That means we train the model using a data set where each instance comes with a known label or an outcome. So the model's task here is to learn from those labeled examples so that it can predict the correct label for new and seen data, right? Imagine we're working with weather data, for example. This is a very known toy data set in machine learning. And the goal is we want to predict whether the conditions will be so based on the weather condition, we want to predict whether or not we go out to play tennis, right? So that's a classification problem. And you can also think in the medical domain when we are trying to decide whether this person has a cancerous tumor or no, right? So based on an MRI scan, for example. So the reason we call this supervised learning is because the learning process is guided by actual outcomes. So the class labels, we provide them during training, right? So we are guiding the learning process. So the model isn't just exploring the data without any aim. It's learning with directions, right? It knows the right answer during training and tries to adjust its internal rules or parameters to match them as closely as possible. So for example, if a record says a customer used a coupon, visited the website, and made a purchase, the model sees the features and the result for this one is purchase yes. So the model will use this labeled instance to improve its decision-making logic in order to predict whether a new customer will purchase or no, right? So in classification, the outcome or the target label is called the class, right? So classes are discrete categories. So think of spam or not spam, right? Cancer or non-cancer. And sometimes in multi-classification problems, there are more than two classes, right? For example, in sentiment analysis, you can predict positive, negative, and neutral, for instance, right? And it's always important to remember that success in classification is not always just about accuracy, right? In many real-world applications, especially in business or medicine, the acceptability of the prediction to a human matters just as much as the numeric score or the accuracy, right? So, for instance, if a classifier detects a fraudulent transaction may be 98% accurate overall, but if it falsely flags a loyal customer, then this damages the trust, right? And this problem could outweigh the benefits of the accurate detection. These are some of the fielded application of classification learning. You can use it in, as we said, in the medicine, weather forecasting, spam detection, and so on. So the next category of supervised learning is regression. So in classification, we predicted discrete class labels, right? Like yes or no, low, medium, high, right? But in regression, our goal is to predict a numeric outcome, right? A quantity. You can think of regression as a variant of classification where instead of putting an instance into a category, we are estimating a value on a continuous scale, right? For example, in retail, we may want to predict how much a customer will spend this month, right? Or the number of items in their shopping cart. Okay, these aren't yes or no questions. These are real numbers. Okay, that's what makes them regression tasks. Okay. So just like classification, regression is supervised. So during training, the model is given not only the input features, but also the correct target value, right? And this value could be a dollar amount, a duration, anything really numeric, okay? As the model trains, it tries to minimize the error or the mistakes that it's making between its predictions and the actual target values, okay? There are specific metrics that we use to calculate this error. And we will discuss these later. So things like the mean squared error or the mean absolute error, and these are used as evaluation metrics to judge the performance of the model. And so we're not just interested in prediction here when it comes to regression. We are also interested in the structure the model learns. That means we want to understand which features are most important for making predictions, right? How do those features relate to the outcome? Is the relationship linear? Is it conditional? Are there any interactions or relationships between features, right? So in regression, it's not just about forecasting or predicting, it's actually about extracting interpretable patterns that link input variables to a numeric outcome. So there are many fielded applications of regression analysis. I listed some right here. Now let's talk about unsupervised learning, right? So far we've introduced supervised learning where each data point has a known outcome, right? But what happens when you don't have those labels? That's where unsupervised learning comes in. So take a look at this example, which is the classical iris dataset, right? This is a very well-known toy dataset in machine learning. So this one contains measurement of iris flowers, things like the sepal length, the sepal width, and so on. Normally in supervised learning, each row has a corresponding species type, like Iris setosa or Versite color and so on. But now imagine we do not have that. We don't have the species of the flower. So we still have all the features. So we do have unlabeled data, but we no longer know which flower belongs to which species. So in this situation, we can't train the model to predict a label because we don't have it, right? What we can do instead is ask the model to find structure in the data. For example, can it group similar flowers together? Can it discover clusters or groups that might correspond to natural species? Can it reduce the dimension of the data so we can visually look at it, right? So that's the job of unsupervised learning. So we're not teaching the model what to look for, we're letting it explore on its own. Okay, so think of unsupervised learning like a student studying from a marked answer key, right? While for unsupervised learning, it's like exploring a new city without a map, right? So just looking for neighborhoods, hotspots based on experience alone, right? So under unsupervised learning, we find things like clustering and dimensionality reduction. So I listed here again some of the fielded application for clustering. Now, association learning is typically used as another type of learning, right? We'll start discovering how do machines learn. So here, we use association learning when no class label is specified again, right? So it's not supervised in the usual sense. Instead of predicting a specific outcome, like in classification or regression, here we ask what combinations of attributes or feature values tend to appear together in the data, right? So the most famous example comes from market basket analysis. So finding patterns like if a customer buys bread, right, and peanut butter, then they are likely to also buy what? Obviously jelly, right? So what sets association learning apart from classification is that in classification, we only predict one target, which is the class label, versus in association learning, we can predict any attribute value. Okay, so this makes it incredibly flexible and also much more computationally intensive. Okay, instead of learning a single rule to predict one target, we may discover thousands of association rules, each describing some potentially useful correlation, right? So things like if the age is young and the coupon is used, then visited websites, yes, right? Or if the product is milk and day is Friday, then they will likely buy diapers. Okay, so things like that. These are some of the fielded applications. It's widely used in retail, in e-commerce, in fraud detection, and we will talk about them in detail in this course. So what does a model actually produce? What's the output, right? How does it represent the patterns it has learned from the data? So the answer is it produces structural output, or what we call knowledge representation. And different learning algorithms actually produce different kinds of models, and those models are expressed in various structural forms. So some of the most common ones include decision trees, right? And rules, tables. So these are all different ways of encoding what the model has learned, right? And the choice of representation is not really cosmetic. It fundamentally affects how the model reasons, right? And how the model predicts and how it explains. And that's why we refer to it as knowledge representation. So it's the form in which the system stores and communicates what it knows, what it learned. Okay, so the type of output will vary depending on the learning problem, right? So for instance, the classification model, it might give us a tree or a rule, versus a regression model, it might give us an equation, or so an equation that describes a line or a hyperplane, right? So then the type of representation that is used will determine the inference method after, right? So how the model applies what it knows to new and seen data. That's inference. So we're going to discover some of the common knowledge representations, some examples here. Decision tables, right? They are simple. They look similar to the data set itself, right? Which is part of what makes it accessible. It uses the same tabular format, right? That we use to represent the input data set, but now we treat the entire table as a structured output model, right? In this case, the table here is showing examples from the weather data set, with the features are the outlook and the humidity, and the decision class is play tennis, yes or no. Okay, so it works, the decision table works by laying out combinations of attribute values and their corresponding predicted outcome. Okay, so when a new instant comes in, say outlook is sunny and humidity is normal, we can look it up in the table and retrieve the predicted class, which in this case is yes, right? So what makes decision tables powerful is their simplicity, right? They're easy to read, they're easy to implement, and they're fully transparent. Okay. The problem is if you have too many features, then the table becomes really bloated. The other familiar form of knowledge representation is linear regression functions, right? Where we are expressing the output as a weighted sum of the input variables, okay? So here we see an example from a real-world dataset involving CPU performance, and the task here is to predict how fast the CPU will run based on hardware characteristics, right? Like the cache size, which is shown here. And so the output of the learning process is actually a formula, right? So each coefficient that we see right here corresponds to how strongly that attribute contributes to the outcome, okay? So some features may have a great impact than others, and the model reveals this numerically using these weights, Okay, so this kind of representation is useful in many domains, as finance, forecasting, and so on. Another type of output is decision trees. So decision trees represent a model using a tree-like structure where internal nodes perform tests on input features, and the leaf nodes, these guys right here out of the leaves, they do represent the outcome, such as the class predicted, okay, or even sometimes probabilities of the class. So the process of building a decision tree follows a divide and conquer strategy. So we start with the entire data set, and then we split it based on the attribute that best separate the data. Okay, so you will have an exercise to practice this later in the course. So once an instance reaches a leaf, then the model produces its output, and that could be sometimes one single classification, or a probability of belonging to a class, and so on. So when you want to classify a new instance, now that you have the tree built, all you have to do is route it through the tree, right? Based on the feature value, starting from the root. This is the root. And making decisions at each of the branches, right? These are the branches. And until you reach a leaf right here, which is the decision or the outcome. Another powerful and interpretable form of knowledge representation is classification rules. Okay, so classification rules offer a very popular alternative to decision trees. So instead of branching through a tree structure, rules actually operate as if-then statements. So each rule takes the form of if condition, then the classification outcome, right? So most rule systems, they are logically and, right? So we apply the and on them. And so let's say condition 1, if condition 1 and condition 2, then outcome 1, right? So all of them must be true for the rule to fire, right? Condition 1 and 2 have to be both true for this condition to be true, right? So in more complex models, the conditions can actually be hard to apply, and so sometimes the predicted outcome may not satisfy all these rules. So it's hard to apply rule-based models to more complex nonlinear data. We've talked about association learning before, and the type of outcome they're producing is association rules. Okay, so it is similar to classification rules, except with classification rules, the outcome is the single class, versus with association rules, we can predict any attribute, not just the label itself. We can predict one attribute, two attributes, all attributes, right? A combination of attributes, and so on, right? So the number of possible association rules will grow exponentially with the number of attributes, right? Because we're trying to find all different combinations to make a decision, and without constraints, if we don't apply constraints to these rules, you could generate actually millions of rules, right? Most of which are redundant or insignificant, okay? That's why when we talk about association rules, we'll talk about how to constrain them, how to apply some constraints to limit the number of generated association rules. we talked about another form of unsupervised learning, which is clustering. And the outcome of clustering algorithms is um, these groups, which we call clusters. So the items within a cluster are more similar to each other, and the items in different clusters are as dissimilar as possible. So in other words, the model captures natural grouping or patterns that exist in the data, right? So even if you didn't know about them ahead of time, right? So the output here is the knowledge that clustering provides, right? It's a partitioning of the data set into meaningful segments or groups, okay? So these groups can be then used later for things like targeted marketing, customer profiling, and so on. So now that we've explored how models represent what they learn, let's turn our attention to an equally important question, which is how do we evaluate what the model learned is actually useful, right? So for classification problems, the most natural performance metric is actually the error rate. So we can ask how often does the model predict the wrong class, right? For each instance in the data set, the model makes a prediction, and then if the predicted class matches the true class, we count that as success. If it doesn't, then it is counted as an error. And once we've processed all instances, we can calculate the error rate, right, as the number of misclassified instances over the total number of instances, right? So this gives us a simple, intuitive way to judge the model's performance. So the lower the error rate, the better the model the better the model is, right? And something to keep in mind is the error rate on the training data is sometimes optimistic or misleading, because a model evaluated on the same data it was trained on, it will almost always look great, right? Maybe even perfect. And this is because it has already seen those instances and may have simply memorized them, right? That's why we say that the training error is optimistic, right? It tells us how well the model performs on known data, not how will it do on new and seen data. And that's what we truly care about. We call this generalization, right? So to get an honest estimate of the model's performance, we need to evaluate on a separate and seen data, okay? The data that the model hasn't seen before. That's where sets like validation set or test set comes in handy, okay? So to properly evaluate the learning algorithm or model, we must divide our data set into three separate parts, okay? So as we see here in this figure, we begin by the full data set right here, which in this case includes things like car insurance premiums, for instance, okay? And their corresponding losses, okay, which were incurred by the insurance companies. So our goal is to use this data to learn a predictive model and test how will it generalize the unseen data, okay? So first we extract the training data, and this subset will be used to actually fit the model, meaning this is the data the algorithm sees during learning. So the model will adjust its own internal parameters to best match these points. And next, we use a separate subset of the data, which is called the validation set. This data is used to train the model, but it's critical during model selection and tuning. So we use the, I'm sorry, did I say used? So I meant it is not used. So here we do not use this data during training, okay? So we use it to select the model and fine tune its parameters, okay? So we use it to compare if we have different models. So we use the validation performance to compare these different models, and we get to decide when to stop training a model, for example, in the case of deep learning. So The other final set or subset is the testing set. So this one is held back until the very end. It plays one single critical role, which is to evaluate the model's performance on unseen data. So here, so you train the model, you predict you evaluate its performance on the validation data. If you don't like it, you adjust the model and you go back to training again. So you are allowed to do this cycle of training, fine-tuning, training, fine-tuning, okay? Only once you are done this cycle completely and you think you have a ready model, then you move to the testing stage, okay? And you test once and that's it. So you are not allowed to go back to train, okay? So then it's up. We use the training data as our learning material, okay? We use the validation data as our practice exam, and then we use the test data as our final exam, okay? So every learning algorithm has a set of parameters it learned from the data, like the weights in a regression model that we've seen before, right? So in addition to those, there are also other parameters that we call hyperparameters that are not learned from the data but are actually chosen by the model's designer, okay? So think of the depth of the tree. So this is a hyperparameter that the designer or the developer chooses, right? So these settings can have a huge impact on the model's performance, okay? If the tree grows too deep, then it might fail to generalize to new data. That's a problem called overfitting, okay? And if it's too shallow, then that's another problem that's called underfitting, where the model is too simple to fit the data, okay? So how do we choose the right parameters and hyperparameters, sorry? This is where the validation set comes in, right? So we use the training set to build models under different hyperparameter settings, and then use the validation set to evaluate and compare them. So the idea is to pick the model configuration that performs best on data that it hasn't seen during training, and that's the validation data, right? So this tuning process is sometimes automated with tools like grid search or random search that systematically try different combinations of hyperparameters, and they track their validation performance. So as you begin evaluating models, cross-training and validation and testing set, one pattern that you will see again and again is that the accuracy tends to drop from one stage to the next. And here is the key message. That is not a failure, that's actually expected, okay? So on the training data, the model performs best. That's because it has been optimized, right, specifically for that training data. It's seen it, it's adjusted to it, and it may even have memorized some examples, right? So then we move to the validation data, which is the model hasn't seen before, right? So here we usually see a drop in performance, maybe a few percentage points. That's normal because the model is now being tested on generalization, not memorization, right? So if the validation performance is close to training performance, this means that the model is likely working well, okay? But if the validation accuracy is much lower, then the model, we say that the model might be overfitting, okay? Which means memorizing the training data patterns that don't apply elsewhere. Okay, in this case, we can use the validation feedback to adjust the hyperparameters or simply the model. Okay, and finally, we test the model on the testing data. Okay, here again, we expect a small further drop in accuracy, maybe 1 to 3% if everything is working properly, right? But if the testing accuracy falls off a cliff, this may mean, again, we over-tuned the model to the validation set, okay? So this drop is a healthy sign that the model is trying to learn patterns that generalize, not just those that fit the training data perfectly. Okay, so that's the overfitting problem. On the other hand, when we say underfitting, that happens when the model is too simple to capture the underlying structure of the data. Okay, it might be missing important patterns, leading to poor accuracy on both the training and the testing set. Okay, so think of it as using a straight line to model a curved trend. Okay, it just doesn't have enough flexibility, right? So in between, we have a good fit, right? This means that the model captures the main patterns in the data without memorizing the noise in the data, right? It performs well on training and generalizes well on validation and testing data never seen before. Okay. So on one hand, we do want one large training set because the more examples the model sees, the better it can learn. And larger training sets improve generalization and they do reduce overfitting and they help the model to capture subtle patterns, right? On the other hand, we also want a large test set so we can reliably evaluate how the model performs on unseen data. A small test set might give a noisy or misleading estimate of the true accuracy, right? But of course, we only have so much data to begin with. Um, every instance we assign to the test set is one less example the model gets to learn from, right? And every record we add to the training set reduces our confidence on how well we've evaluated the model, right? So this creates like this tension. Do I train better or test better? Okay. The standard practice here to answer the question is to split your data. Okay, so while the exact percentage may vary depending on the dataset size, but most data mining workflows follow a conventional split between training, validation, and testing, as we said. A common rule is 60% for training and 20% for validation, right? And the other 20% is for testing. So giving the model enough data to learn from, so we have 60 to even 80% sometimes, okay? And we do have enough data to tune it, okay? And we also are holding out enough data to get a trustworthy final exam or final evaluation.